Hi, let's talk about enzyme kinetics. First, let's start with velocity and maximum velocity. Let's do one experiment. Let us say you are a scientist and you have taken different concentration of substrate in different flasks. The concentration of substrate increases from flask S1 to S7, while the concentration of enzyme added to each flask is constant. So let's say this is the enzyme present in the flask. As you can see, the concentration of enzyme added to each flask is same, whereas the concentration of substrate is increased from flask S1 to S7. So in this figure, this is the free enzyme, the red dot represents the substrate, and this one over here represents the enzyme substrate complex. As the given reaction proceeds, the substrate gets converted into product and the product is released. The amount of product formed per unit time is called velocity of the reaction. As the substrate concentration is increased from S1 to S5, the velocity is increasing. This is because the amount of product formed per unit time increases with increase in substrate concentration. So the velocity increases with increase in substrate concentration. At very high concentration of substrate, the velocity becomes maximum. This is known as maximum velocity or Vmax of the reaction. So the graph of the reaction will appear something like this. The initial part of the graph is the straight line graph. As the substrate concentration increases, there is increase in velocity. This increase can also be seen in this figure. As the substrate concentration increases, there is more and more amount of product formed per unit time. That is, velocity increases with increase in substrate concentration. At high substrate concentration S6 and S7, there is no further increase in velocity. Hence we say the velocity has reached its maximum limit. In short, this is known as Vmax. Now, this linear increase that you see in the graph is classified as the first order kinetics. So this whole increase that you see in the figure is the first order kinetics. This part of the graph where the line becomes flat is known as zero order kinetics. The zero order kinetics can also be defined as the phenomenon in which the velocity of the reaction is no longer affected by increase in substrate concentration. You keep on increasing the substrate concentration, but there is no increase in velocity. So zero order kinetics is a situation where Vmax is reached. So this part is the zero order kinetics, which shows with further increase in substrate, there is no increase in velocity. So mathematically, the reaction is represented in this form. The free enzyme reacts with the substrate and forms the enzyme substrate complex. This ES complex is further broken down into free enzyme and the product. Now, if you see this reaction carefully, then you can see the product is formed by the breakdown of ES complex. In other words, the product formation depends on the ES complex. So, more is the amount of ES complex, more is the velocity. At high concentration of substrate from S6 to S7, the ES formation has reached maximum. Hence, there is no further increase in ES complex. This is a stage where Vmax has reached. So, more is the amount of ES complex, more is the velocity. Hence, we say V0 is directly proportional to ES complex. And Vmax is reached when there is maximum ES formation. Hence, Vmax is directly proportional to ES maximum. Later on in this video, we will see what ES maximum is. Now, let's understand what is Km. So, this was our experimental setup. And this was the point where we had the Vmax. Now, to find the Km, we find the substrate concentration at which the velocity is half of Vmax. If we carefully analyze substrate concentration S3, then this is the flask where the velocity will be half of Vmax. Hence, Km value will be S3. Now, pay attention to this part. Km can also be defined as the substrate concentration at which 50% of the enzyme molecules are saturated to form ES complex. So in other words, Km can also be defined as the situation in which you have 50% of ES formation. Now let's talk about enzyme concentration in system, that is free enzyme and the total enzyme. So the system that you see in here, we have the ES complex and the free enzyme. So the total enzyme E0 can be given as free enzyme E plus ES complex. So this is the total enzyme E0, this is the free enzyme, and this one over here is the ES complex. Now let's go one step further. When Vmax is reached, we have maximum ES formation. When Vmax is reached, there is no free enzyme left in the system. If you see this carefully, in this situation, there is no free enzyme left. So in this equation, when Vmax is reached, free enzyme E becomes 0. So E0 becomes equal to ES complex, and this is a situation for Vmax. Now if you can recall, previously we have seen this equation which says Vmax is directly proportional to ES maximum. And this ES maximum, the one that you see in here, is nothing but the total enzyme E0, because ES maximum is equal to E0. So this equation can be modified as Vmax is directly proportional to E0. Your E0 is equal to Es maximum. Now, when we say maximum velocity depends on E0, this means if you increase the concentration of enzyme, then the maximum velocity will increase. In other words, in a system, if you add more amount of enzyme, then the maximum velocity of the reaction will increase. However, in both the cases, the value of Km will be same. This is because the value of Km is constant for each enzyme. Now let's talk about equations for enzyme kinetics. So this is what we have seen before. The free enzyme reacts with substrate, it forms the ES complex. This one is broken down to free enzyme and the product. Now, for the forward reaction, the rate constant is K1. For the reverse reaction, the rate constant is K minus 1. And the rate constant for the breakdown of ES complex into enzyme and product is K2. Now, we have also seen the product formation depends on ES complex. So, V0 is directly proportional to ES. Now, if you remove this proportionality, then this has to be replaced by the constant. So, V0 is equal to K2 into ES. Your K2 is a constant which represents breakdown of ES complex to form free enzyme and product. Then we have also seen this scenario that when Vmax is reached, the total enzyme E0 becomes equal to ES complex. So Vmax is equal to K2 into E0. This equation over here has been modified to this when Vmax is reached. This is because when Vmax is reached, E0 becomes equal to ES. So this ES over here is represented as E0. And these two are the most important equation that all of you should remember. Always remember Vmax depends on E0, V0 depends on ES. Now let's move further and try to understand the concept of steady state and pre-steady state. The enzyme substrate complex remains in equilibrium. This means the rate of ES formation is equal to rate of ES breakdown. So the rate at which the enzyme and substrate reacts to form ES complex is same as the rate of breakdown of ES complex in the reverse direction or in the forward direction. And this is known as the steady state hypothesis. Then we have something which is known as the pre-steady state hypothesis. This is a stage where the enzyme and substrate are just mixed and they react to form the enzyme substrate complex. The pre-steady state remains for a very short period of time. Now, the steady state hypothesis is very important. When we say rate of ES formation is equal to rate of ES breakdown, then in this reaction, ES is formed by the reaction between enzyme and substrate, and the rate constant over here is K1. So we write K1 into E into S is equal to the rate of ES breakdown. ES is broken down into reverse direction to form ENS, or this ES can be broken down to form ENP in the forward direction. So if this reaction goes in reverse, then the rate constant over here is K minus 1. So we write K minus 1 into ES plus K2 into ES. So this whole part represents breakdown of ES complex. Now if we rearrange this equation, then this will be the equation for Km. Km can also be defined as the ratio of rate constant of enzyme catalyzed reaction. If you see this carefully, Km is the ratio of rate constant of breakdown of ES complex versus rate constant which forms the ES complex. Now let's talk about Michaelis Menten equation. So this is what we have seen before. E into S divided by ES is Km, and you can imagine this reaction happening in this form. This is the free enzyme, this is the substrate, this one is the ES complex. We are taking this ratio and this is Km. Now, the total enzyme E0 is equal to free enzyme E plus this ES complex. So the free enzyme over here, which represents this part, this has to be replaced by this one. So E is equal to E0, the total enzyme, minus ES complex. So the value of E can be replaced here and we get this equation. First, multiply this S with this and this. Now rearrange the equation in blue to get this one. So in this, these two ES will be cancelled out and we get this equation. The equation that you see here, this minus S can be taken on this side. So we get this. Now we need to solve the equation for E0. Your E0 can be written as the ratio of Vmax divided by K2. So this E0 over here is written as Vmax divided by K2. However, if you see this part of the reaction, this product will form V0. So this whole part can be replaced by V0. So do not be afraid of this equation. It is extremely easy. Once you practice it, you can solve this equation in few minutes. Now let's talk about enzyme inhibition. First, let us discuss about competitive inhibition. Let's do two experiments. The first one is the control experiment, which is without the inhibitor. The second one is in presence of competitive inhibitor. As the name suggests, the competitive inhibitor will compete with the substrate to bind the active site of the enzyme. So, at the initial stage, where the substrate concentration is very less, the competitive inhibitor will bind with the enzyme and form EI complex. So in this flask, where the substrate concentration is minimum, we have maximum EI formation. Now, as the substrate concentration is increased, the competition between the inhibitor and the substrate will also increase. As a result, more and more substrate molecules will bind with the enzyme to form ES complex. If you see this figure carefully, then because of competition, we require more amount of substrate to saturate 50% of the enzyme molecules to form ES complex. So in other words, the Km value increases in presence of competitive inhibitor. The Km value in absence of inhibitor was S3, and in presence of competitive inhibitor, the Km value has increased to S5. So in absence of competitive inhibitor, the substrate concentration S3 showed 50% formation of ES complex, whereas in presence of competitive inhibitor, the substrate concentration S5 shows 50% of ES formation. Now the question is, what about the value of Vmax? Let's recall. Vmax depends on total enzyme concentration. In simple words, Vmax depends on maximum ES formation. So in this case, the control as well as in presence of inhibitor, the maximum ES formation is same. So Vmax will be same in both the cases. However, if you notice carefully, then the substrate required to reach the Vmax has increased in presence of competitive inhibitor. Remember, the value of Vmax is unchanged, but the amount of substrate required to reach the Vmax has increased in presence of competitive inhibitor. So let's try to understand the graph. This is the control in absence of inhibitor. And this one, the dotted line that you see in here, is in presence of competitive inhibitor. So in presence of competitive inhibitor, the value of Km has increased. However, the value of Vmax remains the same, but the amount of substrate required to reach the Vmax has increased in presence of competitive inhibitor. So, according to this principle, in the reaction that we see here, if we increase the amount of enzyme, then this will increase the forward reaction. Also, if we increase the amount of substrate, then again it will increase the forward reaction to form more amount of ES. Further, if you increase the amount of ES, then the reaction will proceed in reverse direction to form more amount of free enzyme and substrate. Let's go one step further. If you decrease the amount of ES, that is, if you take away this, if you're taking away this, then these two, enzyme and substrate, will react to form more amount of ES. In other words, if you take away ES, then the reaction will shift in forward direction. Let us try to understand the same thing in more creative way. So the enzyme reacts with substrate, it is forming ES complex, and this whole reaction is under equilibrium. So this is the free enzyme, this is a substrate, and this is the ES complex, and the rate at which the substrate reacts with the enzyme is equal to the rate at which the substrate is released from the enzyme. So this whole phenomenon is under equilibrium. Now, if you increase the substrate concentration, then more amount of substrate will react with enzyme and form more amount of ES. So the reaction goes in forward direction. Now let's say a situation where you remove the ES complex from the system. So this is ES formation, and if you remove this, then the substrate is going to react with enzyme and form more amount of ES. So this is how the system tries to restore the equilibrium. If you remove this, then these two will react to form more amount of ES. This is what all of you should know. So whenever there is a reaction between enzyme and substrate, this whole reaction remains in equilibrium. You will have ES complex, you will have free enzyme, and you will also have free substrate molecules because the system tries to remain in equilibrium. Now let's understand uncompetitive inhibitor. So the uncompetitive inhibitor is the one that reacts with enzyme substrate complex. Remember, uncompetitive inhibitor reacts with ES complex. So let's say this is the reaction setup without inhibitor. This one is the Vmax. So this is maximum ES formation, and this one is going to give us Vmax. And this is the Km where 50% of ES is formed. So as the uncompetitive inhibitor is added, it binds the ES complex. Since the inhibitor binds the ES complex, the concentration of ES complex in this whole system goes down. Remember, when the uncompetitive inhibitor binds the ES complex, the concentration of ES complex in the system will go down. So this whole part is inhibited and we have only this much amount of ES complex left. So as the concentration of ES complex decreases, according to Le-Chatelier's principle, the enzyme and substrate will react to form more amount of ES. So as the reaction shifts in forward direction to regain the equilibrium, these substrate molecules which are free will react with the enzyme to form more amount of ES. So let's see the animation to understand how the reaction moves in forward direction. So this is a situation when the equilibrium is re-established. Now let's try to find out Km and Vmax of uncompetitive inhibitor. So this whole portion that you see is inhibited. So this is a point where we will have maximum ES formation, and this will be our Vmax. Now since this portion over here is all inhibited, only this portion will give rise to Vmax. So because of this inhibition, the value of Vmax has decreased. So instead of having this much big Vmax, we have only this much Vmax. Because since this is inhibited, only these many ES molecules will give us maximum velocity. So in presence of uncompetitive inhibitor, the value of Vmax will decrease. Now let's talk about Km. Km is the substrate concentration at which 50% of the enzyme molecules forms ES complex. So at substrate concentration S2, we have 50% of ES formation. So if you compare this with the control where there is no inhibitor, then in presence of uncompetitive inhibitor, the value of Km has decreased. So to conclude, in presence of uncompetitive inhibitor, the value of Vmax as well as the value of Km will decrease. Now let's discuss non-competitive inhibitor. Let's say this is the reaction condition in absence of inhibitor. This one is our Vmax, this one is our Km. So when the inhibitor is added, the inhibitor binds the ES complex as well as it binds the free enzyme. So this one is the binding with ES complex, this one shows binding with free enzyme. So in presence of non-competitive inhibitor, this portion as well as this portion will be inhibited. So since this portion is inhibited, this portion over here is also inhibited. The maximum amount of ES has decreased. In other words, in presence of non-competitive inhibitor, the value of Vmax will decrease. Now let's talk about value of Km. So this is a situation in presence of inhibitor. At substrate concentration S3, we have 50% of ES formation. Let's see the control one. Even in absence of non-competitive inhibitor, the 50% of ES formation was happening at substrate concentration S3. So, in presence of non-competitive inhibitor, the value of Vmax decreases but the value of Km remains the same.